Good morning. Thank you very much to the organizers for allowing me to give a talk here and also for changing the topic of my talk on short notice. The talk about 4-point correlators that you find in the program, the numerical results are not quite ready. So I thought I would rather tell you some work on quantum criticality in heavy fermion systems. So this is new work. It's not yet published. All the more, I'm looking forward to discussions and feedback about it. So it was done in collaboration with Gabi Kotler and Seung-Soo Lee, by Andreas Gleis, a PhD student in my group, who's really the main driver. He's here. He has a poster on this topic also. So if you find it interesting, please visit his poster. And it's about heavy fermion systems, where you have localized electrons and delocalized electrons hybridizing, so that you get an interplay between Kondo type correlations and RKKY type correlations. And our main results that I want to tell you about is that we identify the nature of the phase transition. It's a continuous orbital mod transition. There's a Fermi surface reconstruction that has been known for a long time, but we clarify the role of Luttinger surface in this story. And we also study the strange metal regime. We show that in this, okay, I should have said we study this in the context of the periodic Anderson model. And we show that there's strange metal behavior at finite temperatures with linear NT resistivity, and quite a number of other details that I will touch upon. So in heavy fermion systems, the basic ingredients that you have localized F bands hybridizing with itinerant conduction bands. There are numerous materials that show this behavior. It's been studied for a long time. And a paradigmatic model for studying that is the periodic Anderson model, where you have itinerant conduction electrons in blue here hopping around on a lattice. We take a 3-dimensional square lattice. And you have localized F electrons on every lattice site, which have a strong Coulomb interaction. They don't move from F site to F site, but they do hybridize with the C electrons. And this hybridization gives them rise to correlations between the delocalized and the localized electrons. And that's the model that our work has been based on. And then you generically get a phase diagram of this type as a function of a tuning parameter V, the hybridization between the F and the C electrons. At large hybridization, you get Kondo correlations where the delocalized C electrons tend to screen the localized F electrons, and so that they tend to become entangled. It's Kondo screening, really. And in a sense, the C electron binds to the localized F electrons, and therefore they get a large effective mass. That's why it gives rise to heavy fermion type behavior. But on the conversely, the F electrons participate. They get some delocalized nature, and so the Fermi surface consists of F and C electrons. So you get a large Fermi surface in that sense. On the other side, when the hybridization is weak, then what's more dominant is that RKKY interactions favor spin singlet formation between neighboring delocalized electrons. So my shaded ellipses indicate which players tend to be entangled. So here you have FF entanglement versus CC entanglement. And so here the F electrons are not strongly screened by the C electrons. They form some type of spin liquid. I will not speculate about what type. But here the Fermi surface is made up mainly from the C electrons, and so you get a small Fermi surface. All right, so that's the generic picture that's been established long ago. And then at intermediate temperatures, you get non-Fermi liquid behavior. Some of its phenomenology is similar to the cuprates with the linear NT dependence of the resistivity, for example. And material where this is nicely borne out is this one here. Here's an experimental plot where the temperature dependent of the resistivity was fitted to a power law, and the exponent alpha is plotted on a color scale. So here to the right and to the left, the color is blue, so this is like a Fermi liquid behavior. And over here in orange, you get the linear and T resistivity. There are other anomalies here, logarithmic temperature dependent for the specific heat, and omega over T scaling for the conductivity, whereas these regimes are characteristic of Fermi liquid behavior. All right, and then additional things that have been studied is if you measure the Hall coefficient as a function of temperature, there's a jump as you cross this transition, which becomes sharper with decreasing temperature. Here's another way to represent the linear and T resistivity in the strange metal regime. And there are also, if you study the optical conductivity as a function of frequency and temperature, and you do a scaling plot of the optical conductivity over omega over T, you multiply it by some power T to the alpha, you get a scaling collapse if that exponent alpha is close to 1. So this is another experimental finding in this strange metal regime. Okay, so this phenology is much studied. There are some very nice experimental realizations of this. All right, and now the question is, how much of this can one understand based on a model, a toy model, but a paradigmatic one such as the periodic Anderson model? And our work was inspired by early work done by KB-Kotler and his collaborators for this periodic Anderson model, which I studied using cellular dynamical mean field theory. So you have an infinite self-consistent bath coupled to an interacting two-side cluster. So it's important that it's not single side, but two-side DMFT, so that you have a possibility for singlet correlation between neighboring F electrons. In our work, we purposefully exclude symmetry breaking solutions. So question of symmetry breaking in the below the transition, that's outside of what we've studied. And the object that you compute is the F and the C electron self energies and some hybridization between them. And now in this two-side cluster approach, of course, you cannot resolve the momentum dependence. So momentum is represented very crudely. There are just two effective momentum regions of the Brillouin zone, one around the gamma point, the other one around the pi point. And but those, so you could say that's extremely crude, but still it's enough to discriminate the type of correlations that show up. So we will see that, for example, once you reperiodize, you can get momentum-dependent structures in the self-energy, etc. All right, so if you do DMFT, and you want to study a quantum critical point, you have to be able to go to very low temperatures and very low energies. And the method that we use for that is the Numerical Renormalization Group, which has a particular advantage that it's done directly on the real frequency axis. And it's been pushed forward in my group for many years, particularly by Andreas Weichselbaum, who's now at BNL, but was with me for many years. So none of this work that I present today would have been possible without his groundwork. And we study this model at a fixed set of parameters. This is a hopping rate, it's a large interaction. We tune EF in such a way that the system is, there's a finite electron density. And the control parameters that I will be tuning is the hybridization and the temperature. And the phase diagram that Andreas found, I will show you later how he found the crossover temperatures looks as follows. So it basically matches the cartoon that I showed initially. So there's a quantum critical point here, a so-called Kondo breakdown quantum critical point, separating a Kondo phase from an RKKY phase. At high temperatures, in green, there's a local moment regime. Then as you lower the temperature, you go through a non-Fermi liquid regime. Well, I'll show later there are this strange metal behavior. And then you, as you go lower down, you cross a Fermi liquid scale on both sides into a Fermi liquid regime. And so this is numerical data. This is not a cartoon. And NRG allows you to go down to really low energy scales, as you can see on this logarithmic scale here. So, and then to resolve what's going on. So one particular thing, as I mentioned in the introductions, the Fermi surface jumps at this quantum critical point as you tune across it. So you can actually plot it. In the Kondo regime, there's a large Fermi surface. It looks sort of smallish here because there's also a filled conduction band, which plus something in addition. And so this is the Fermi surface for what's happening beyond the filled band. And it's defined by the locus of points in the Brillouin zone where the C electron Green's function at zero frequency diverges. And the same is then true also for the F electron Green's function at that point. On the other hand, in the RKKY phase is a small Fermi surface. It looks larger here because of the way it's been represented, but it really contains fewer electrons. And in addition, there's also a Luttinger surface. A Luttinger surface is a surface at which the F electron self-energy diverges so that the F electron Green's function is zero. And this Luttinger surface plays a key role. So the reason one has to think about it is there's a Luttinger sum rule that relates the density to the Fermi surface. And when the Fermi surface jumps, then the question is, what happens to this Luttinger sum rule? Intuitively speaking, it jumps because here you have Kondo screening, so the F and the C electrons both participate. And here you don't have Kondo screening, so only the C electrons participate in the Fermi surface. All right, so in this slide, I'm trying to clarify how it can be that the Fermi surface jumps, although the electron density evolves smoothly across the transition. Now, there's a very famous Luttinger sum rule going decades back. For one band models, it looks like this. The electron density is related to the volume of the Fermi surface and a certain integral called the Luttinger integral, according to this Luttinger sum rule. Both these quantities are expressed as integrals over the Brillouin zone. And this one, if the system is a Fermi liquid, basically discounts the volume of the Fermi surface. And this is another term which can be shown under quite general conditions to vanish. That's the content of Luttinger's work. That is Luttinger integral generically, well, at least in the perturbative treatment and with some general assumptions, vanishes. And now the question is, what happens if you have a two-band model, such as the periodic Anderson model? And then Andreas was able to generalize this and express the sum of the F and the C electron density in terms of three terms. In addition to the Fermi surface volume, there's another term, Luttinger surface volume. That is the volume enclosed by the locus of points at which the F electron self-energy diverges. And then there's another term, again, akin to the Luttinger integral over here, but now referring to the F electron Green's functions. And we didn't try to study generally when this vanishes, but for his numerics, it does vanish. All right, and now the fact that there's this extra Luttinger surface volume, that is the reason why you can have a jump in the Fermi surface volume without the density having a jump. And this is his numerical results for this. So let me walk through the slide. The green line gives you the total density as a function of the tuning parameter. As you see, it evolves smoothly across the phase transition. The Luttinger integral always remains zero, as just mentioned. Now the blue line here, that gives the volume of the Luttinger surface in the Kondo regime. It's actually equal to 1, which means it fills the entire Brillouin zone. So there's no Luttinger surface over here. And then the Fermi surface volume is shown here. This value is modulo 2. So this, as I mentioned, there's a filled band altogether. So overall, this represents a large Fermi surface. And then on the other side, When you go here, then the volume of the Luttinger surface jumps. It actually becomes equal to 1/2 of the density of F electrons, which is around 1/2. And correspondingly, the volume of the Fermi surface can also jump in such a way that there's some evolve smoothly, all right? So this clarifies how you can have this Fermi surface jump. It's a Luttinger surface that compensates for the difference. All right, now let me explain a little bit about the band structure, how the band structure evolves as a function of interaction and tuning. So this color scale plot shows you the A of k and omega, the spectral density. And initially, without interaction, without hybridization, you just have an F band and a C band. And this would be the Fermi surface that you get in that case. If you turn on hybridization, you open up a hybridization gap. And so the Fermi surface shrinks a little bit. If you then turn on interactions, the bands get renormalized, but the Fermi surface remains fixed by the Luttinger sum rule. This is on the Kondo side. Let's go to the RKKY side. Again, start without interactions, without hybridization. If you now, if you first turn on interactions, then the F electrons get gapped out. And you get the Luttinger surface because this gap of the F electrons means that the F electron self-energy diverges. And if you now turn on hybridization, the Luttinger surface stays put because of the, and the Fermi surface also. And it looks like the band structure does not change much, but that's because we're looking at it at the very large frequency scale. So on the next slides, let me zoom in. So I show you now, basically these plots, but zooming in on the frequency scale. So this is on a scale from 10 to the -1 to 10 to the -10 to the -0.1 to 0.1, and then we go down 1 pair of frequency and another 3 pairs of frequency. So what you see is over essentially 2 bands. So it's hybridization of the F and the C bands. And as you zoom in, you can see that there's that it basically looks like this. All right. So I'm just zooming in more and more closely, and the numbers 1 and 2 just label these 2 bands. This is the Kondo phase. In the RKKY phase, initially it looks like there are only 2 bands, but if you zoom in sufficiently closely, you notice that there's a 3rd band over here. And in my cartoon, I'm trying to emphasize what's really going on. So there's a 3rd quasiparticle band that shows up once you've, due to this Luttinger surface. So that is one of the main messages, this existence of a 3rd quasiparticle band in the RKKY regime. All right, so if you compare them like this, at high frequency scales, similar features seem to happen in the RKKY and the Kondo phase. Differences only become visible at extremely low scales. And now the origin of this extra 3rd band is, and also of the Luttinger surface, is a pole in the quasiparticle self-energy. So let me show that. Here, this is now another plot of the band structure, but on a scale where the large energy regime between 10 to the -4 and 0 is on a logarithmic scale, and then in between is a linear scale so that we can see what's going on there. And you see on the Kondo side, the band structure gets washed out quite a bit as you get close to the critical point. Then you go to the RKKY side, the position where it cuts 0 jumps. That's another way to see it, the Fermi surface jumps. All right. And the origin of that you can find in the F electron self-energy. On the RKKY, on the Kondo side, it is essentially featureless near 0 frequency, but in the RKKY side, it has this strong pole here, which is dispersing. It depends on momentum. All right, so that's not what you get in a MOT phase where the self-energy has a pole throughout the Brillouin zone. It's actually a dispersing pole. And so that's another key conclusion for us. The RKKY phase is an orbital selective MOT phase. The F electrons do something quite different from the C electrons. And actually only part of the F electrons, part of the Brillouin zone participates. And its defining feature is a momentum-dependent pole in the F self-energy. All right, now to physical observables, one can compute the Hall coefficient using the standard tools of DMFT, and one finds phenomenologically something quite similar to what has been observed experimentally, a step as you cross the transition that becomes sharper as you lower temperature. All right, now, how did we extract these crossover scales? What Andreas did, he studied many susceptibilities. It's a function of frequency. I will focus here on the F orbital magnetization and the staggered F orbital magnetization, and plot the imaginary part of those susceptibilities as a function of frequency at 0 temperature. And you find that the red curve for the F orbital magnetization has a peak at quite large frequencies. This is Kondo screening. This defines the onset of the non-Fermi liquid regime. And then it goes down linearly as frequency goes to 0. And in contrast, the staggered F orbital magnetization has a plateau. And the boundaries of the plateau, they define basically these two scales, T non-Fermi liquid and T Fermi liquid. And as you would tune yourself closer and closer transition, this plateau moves over to 0 frequency all the way. So this is how one extracts those scales. All right, and so the conclusion here is these two susceptibilities get screened at different energy scales. So you have a two-stage screening happening. And this plateau here is reminiscent of, well, it's characteristic of this over-screening in the non-Fermi liquid region. And it's reminiscent actually of what happens in two impurity Kondo models or two-channel Kondo models for those that know those models. All right, now, something very similar happens for the optical conductivity. So to lead into that topic, let me show you now how the plateau that I showed you in the previous slide, how this plateau emerges as one lowers temperature. This is a 0 temperature plot, but now I will start from high temperatures. And the color scale, these red bars on the color scale tell you at what temperatures you are. So as we lower temperature, you see that how this plateau emerges. And it basically stops only when the temperature reaches the Fermi liquid scale. Sorry, this was too fast. All right, so basically to summarize what this plot shows us, in the non-Fermi liquid region is between these two temperatures, you have a plateau, and below that, there's omega over T behavior. All right, so it gets cut off at temperature, and below that it's linear. So this is a characteristic behavior here. Now, for the optical conductivity, you would like to know this unique susceptibility of the current correlations divided by omega. Okay, so the current correlations, chi double prime for the current, shows a similar plateau, so it's very, very related. And now if you manipulate it so that you multiply by temperature and over here for the conductivity you have to divide by frequency, then this plateau, this drop here becomes a flat line basically. So it's frequency independent until you reach the Fermi liquid scale. And if you now again go through the different frequency, the different temperatures, you get a plot that looks like this. So you get constant at low frequencies, and then T over omega behavior for T times the optical conductivity. All right, and that has a consequence for the resistivity. Resistivity is 1 over sigma. If T times sigma is constant over here, that means that the conductivity will go like 1 over T. So sorry, that the resistivity will go, if sigma goes like 1 over T, then the resistivity will go linear in T. So that's the claim, why this data implies linear in T resistivity. And another point is, in the introduction, I mentioned this omega over T scaling for the optical conductivity. This plot here is scaled in the same way as over here. T times optical conductivity plotted versus omega over T. And so this scaling behavior that we see here qualitatively matches what is seen over there. So that's the origin of my claim that we get this strange metal behavior in this model in the non-Fermi liquid regime. So final plot, another manifestation of strange metal behavior in experiment is a log T behavior of the specific heat. And okay, this plot is not arranged in the same way as that one, but for the green and the yellow curves that are close to the quantum critical point, these dashed lines indicate log T behavior, and so the colored curves basically match that. And so essentially, we claim that we in our model find this log T behavior also. All right, so with that, let me wrap up. The main message is within the periodic Anderson model, using cellular DMFT plus NRG, we believe we capture several of the paradigmatic properties of this model. In particular, we were able to clarify the nature of this quantum critical point. It's of this transition is a continuous orbital selective Mott transition. The Fermi surface reconstruction goes hand in hand with the appearance of a Luttinger surface, and we have clarified how the sum rule needs to be modified, or how to modify it to account for that. In the RKKY phase, there's a third band showing up. There's a two-stage screening if you go from large temperatures to low ones, and we find strange metal behavior. And many other questions remain to be addressed. In particular, what's the nature of the RKKY phase? What is the role of the Luttinger surface for dynamics? And looking a little bit further ahead, what about pairing correlations, or doing similar studies for example, the 2D Hubbard model? So thanks for your attention, and I'm looking forward to your questions.